Hello students, good morning. Let us start the AEC class. In the yesterday's class, I was explaining this particular block diagram to you, and I was telling that the obvious advantage of negative feedback is increase in bandwidth in spite of the reduction in gain. As such in life, whenever we want to gain something, we should be ready to lose something else. Gaining everything is impossible as such in nature as well. So here in this particular circuit, if you have to have a larger bandwidth, we should reduce the gain, and we reduce the gain purposefully here by applying negative feedback. Please recall whatever I had discussed when I discussed two curves, two frequency responses, one with the larger gain and one with the lesser gain, and I had shown you how the gain bandwidth product is going to be constant for a given amplifier. So if the gain is reduced, naturally the bandwidth will be increased because the points at which we mark those 3 dB cutoff, that is going to be expanded and we will have a larger bandwidth. That is one obvious advantage. Now, please recall whatever I had told yesterday, A equals V0 by Vi. Similarly, beta equals Vf by V0. I should again tell you, this beta is not the beta that is related to the device. This beta is now related to this block diagram, where this is now the feedback factor. So beta equals Vf divided by V0. Actually, Vf is a small portion of V0. So beta will be always less than unity, whereas A will be always greater than unity. We should remember this. A is anyhow greater than unity, that we know. So now A is also called as open loop gain, because without the feedback, it is an open loop now. Once you connect a feedback, we are creating a loop now for the signal to come back. So A is also called as open loop gain. Now our effort will be to find out the closed loop gain. Means when we apply the negative feedback, to how much extent the gain is going to get reduced, that we are going to see anyhow now. So A equals V0 by Vi and beta equals Vf by V0. Beta is less than 1, A is greater than 1. Now we are applying a negative feedback. So here Vi is Vs minus Vf. So these many things if you understand, that is enough. Always remember, Vi is Vs minus Vf. That means the actual input to the amplifier is less than the input signal that is given from the signal source. Because from the input signal, a small portion of the output is going to be subtracted. That Vf is subtracted from Vs. So Vi will be less than Vs. So Vi is equal to Vs minus Vf. And because we are subtracting, now this is called negative feedback. If at all we add, then it is called as positive feedback. That positive feedback we will see later on. Right now we are focusing only on negative feedback. So with this brief recap of whatever we discussed yesterday, let me continue now for today's discussions. Now I am showing you something that is listed in the textbook. You can see this here now. If the feedback signal is of opposite polarity to the input signal as shown in the above figure, negative feedback results. Although negative feedback results in reduced overall voltage gain, a number of improvements are obtained. Among them being, the first one is higher input impedance. The second one is better stabilized voltage gain. The third one is improved frequency response. The fourth one is lower output impedance. The fifth one is reduced noise. The sixth one is more linear operation. Now let me explain a little more about all these 6 advantages of negative feedback. See, one obvious disadvantage of negative feedback was that reduction in voltage gain. But we have 6 advantages. Ideally, any amplifier should have a high input impedance and low output impedance. Now, practically, any particular amplifier will not be able to give all these ideal characteristics. But by applying negative feedback, input impedance also will increase, output impedance also will reduce. Means the closed loop input impedance will be higher than the open loop input impedance, and the closed loop output impedance will be lower than the open loop output impedance. We have later on the mathematical derivations for the same. Later on we will see how that is exactly happening. Now, let me come to the second one, better stabilized voltage gain. Let me show you a curve here. So, in general, the frequency response will be like this, in general, where x-axis is F and y-axis is AV. In general, the frequency response will be like this. But we cannot say that the frequency response will be flat for all the circuits. Later on in the 4th semester, you will study the op-amp circuits. There you will understand something called poles and zeros, that you are going to study in detail in one more course called control systems, where you will understand more about the effects of feedback. Control systems is more about the block level discussion of these engineering systems, not just electronic systems. It is applicable to any engineering system. So there you will study something called poles and zeros. They are basically terminologies that are used in the mathematical analysis of the frequency response. So I cannot deal with poles and zeros as of now, because it is going to be covered later on in next semester only. So, when there are poles and zeros in the circuit, the poles are going to introduce instability in the system, and the instability is going to cause a non-linear frequency response. Means, instead of this particular curve, somewhere you may get something like this. Let me use a different color. Now you may get a frequency response. It may go like this, and it may come back like this. And you can see this area. In this area, the gain is not flat. Even though we measure 3 dB here and here, we can measure FH and FL here. This can be now FH, and this can be now FL. This is fine. But you can see here, this particular portion, let me change the color again. Now, at this particular portion, you can see that the gain is not uniform. Now, you may wonder why the gain is not uniform. Now, here, you can see the frequency which is in the increasing order. The device may not have flat response for these frequencies now, because we don't know the circuit parasitics. We had seen all these things in the previous module about in high frequency analysis, what all other parasitic components are coming into picture. All types of junction capacitances, transition capacitances, they are all coming into picture. So in such a case, at very high frequencies, the device's internal parasitic capacitances may introduce some other response, due to which the gain may be affected. At some frequencies, the gain may go to higher range and it may come down. The reverse is also possible. That means the gain may come down at a particular frequency range. You have already studied a course called network analysis, and I think you have already come across a concept called resonance. In the case of resonance, when XL equals XC, resonance is going to happen. or else when the resistances and reactances are equal, then also resonance is going to happen. There are inductive and capacitive reactances in a circuit. So in general, there is also something called a series resonance and parallel resonance, where reactance or impedance, not just reactance, impedance can be minimum at a certain point or impedance can be maximum at a certain point. Now, what do you understand by this particular point where the gain is increasing? When the gain is increasing at a particular given frequency, let us say in this particular frequency, gain is increasing here. Now, the gain is increasing, that means that the net impedance of the circuit is reducing. When the impedance is reducing, suddenly gain can increase. Now, we thought that impedance is supposed to be constant throughout. But at higher frequencies, impedance also need not be constant. Why? Because at higher frequencies, parasitics are coming into picture. For example, I should give a real life example to you. During daytime, let us say at your home, all of you are active. Now, during daytime, you will not see much of cockroaches moving or the lizards moving. You will not see all these insects moving within your house. But during night time, when you are sleeping, all these cockroaches or lizards, they will come out, especially cockroaches and all the nocturnal insects. They will come out and they will be searching for their food. At night time, if you go to kitchen, you will see that there are cockroaches in many corners there searching for some left out food material. You may also see that these cockroaches are making strange noises even inside the dustbins also. Now, in the daytime, when everything was having noise, you would not notice the noises that are caused by these cockroaches. But at night time, when everything else is silent, you can even listen to the noises that are made by these cockroaches inside the almirahs or inside the wardrobes or even inside the dustbin, inside the kitchen, everywhere. What does it mean? It means that when everything is silent, even a small noise is also going to be predominant. When everything is silent, even a small noise is going to cause its own effect. That was a real life example. In the same way, in case of these electronic systems, at high frequency ranges, even the smallest possible parasitic elements are also going to play their role. They could be ignored at the lower frequency ranges, but they cannot be ignored at the higher frequency ranges. So, a point where I am telling you, let us say this particular point, wherever I am telling, the gain has suddenly gone up, means the gain is increased. So, this increase in gain is due to the reduction in impedance at that time. The reduction in impedance may happen at that time because resonance will happen within the circuit there. That resonance is again because of the parasitic elements there. Now again this resonance can be reduced by means of something called frequency compensation. You are going to study about the frequency compensation methodologies in the other courses in the higher semesters. Because in the third semester, we will be discussing only the basics or our requirements in circuits. Later on, if you are remaining in the technical domain only lifelong, then you will come across all these things in all the electronic designs, even in future. When you start working in industries also, you will come across all these situations, provided you are working in the core industries only. Okay, you have multiple options when you come to third year and final year about which career you should choose, or whether you want to establish your own entrepreneurship or you want to go for higher studies. You have multiple options. But if you remain in the core domain of electronics and communications, then all these bases are going to play a much bigger role where you will be dealing with them even in your future designs. So, this particular area where there is a difference in gain, that is because of the non-linearity of the circuit at higher frequencies. Now, because of this non-linearity, voltage gain can be having differences. Now, obviously, when we apply negative feedback, what happens? When we apply negative feedback, the gain gets reduced, right? Let me change the color. When we apply negative feedback, now the gain gets reduced. Now, when the gain gets reduced, curve will become like this. Let us say, even though there is a slight offshoot here, I am showing you a small offshoot here. That means a slight increase. That increase can be ignored at that time. Even though at this particular point, parasitics may become dominant, but the overall gain is now reduced, right? Let us say the upper curve was corresponding to the open loop gain. The lower blue line is corresponding to the closed loop gain, that is with the negative feedback. When the gain is reduced, even these non-linearities also get reduced, and that is what is meant by better stabilized voltage gain. And I have already discussed the improved frequency response yesterday itself. That means now we will have these 3 dB cutoff points marked somewhere here. When you have 3 dB cutoff point marked somewhere here, you can see that there is increase in bandwidth. That is improved frequency response. Regarding lower output impedance, I have already told that later on we will have derivations for the same. Now, reduced noise. What does it mean by reduced noise? When the gain is larger, automatically at times even the noise also will be amplified along with the signal. Later on in other courses, you are going to study about the design of filters and how we use filters so as to filter or suppress the noise. Okay. But even at times, filters will not be able to completely suppress the noise if the noise is internal to the amplifier. Even the amplifier itself can generate its own noise. Even the transistor itself can generate its own switching noises. We are going to study about noise in detail when you come to third year. I am talking about the electronic noise. Okay. So when the gain gets reduced here, the noise also is going to get reduced because the amplification of the noise also is going to be lesser. Finally, more linear operation. More linear operation basically means whatever I told here, that sudden offshoots which are there in the frequency response will not be there with the reduced gain or with the negative feedback. That is called as more linear operation. So, of course, this 6 is same as 2. Okay. And this 5 is again almost related to 2, because when there is a better stabilized voltage gain and when the gain is reduced, noise is also reduced. So that way you remember distinctly 5 advantages: higher input impedance, lower output impedance, higher bandwidth and stabilized voltage gain, reduced noise. Finally, all these things are leading to more linearity in the frequency response or even in the gain response. So, these are all the advantages of the negative feedback. So, now let us see how can we have different types of feedback connections. Now, I'll just show you these types. We basically have 4 types. Just for a change, starting from yesterday's class, I am showing you the pages of the textbook directly, purposefully, so that at least my students let them see the textbook. Because I am not sure all of my students will be studying from the textbook. Mostly you are dependent on the notes or the PPTs which teachers give you. So I thought we are having 2 beautiful textbooks. One is Malvino and one is Boyle Stud. Right now I am showing you the textbook written by Boyle Stud. It is one of the very useful textbooks for this particular course. Not only for this particular course, for all other understandings of the basics of electronics and communications. In the yesterday's class, I had told you that you should have a personal copy of Electronic Principles by Malvino and you should keep it with you lifelong if you love electronics and communications. Okay. So purposefully I am showing you the textbook now. Later on anyhow, whatever is the notes written by me, I will neatly put it in my PPT and I will present it quickly when I cover all these portions at some depth. So there are four feedback connection types: voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback. Which means, let us say we sample the voltage from the output side and we give it in series to the input. Then it is called voltage series feedback. On the other hand, let us say we sample voltage from the output, we give it in parallel to the input. That is called voltage shunt feedback. Further, we take current from the output and we give it in series with the input. Then that is called current series feedback. Lastly, we take current from the output, we give it in parallel to the input. That is called current shunt feedback. I will show you the diagrams now. You can see this diagram. Now you can see you have the load resistance here, and I have already told you that A equals V naught by Vi and beta equals Vf by V naught. So Vf is equal to beta into V naught. And you can see in this particular diagram, you can see voltage is taken from the output. Output voltage itself is taken. It is given to a feedback network. This feedback network is basically an attenuating network. It is a passive network, so to say. Passive network in the sense, in this feedback network, there is no active device. There is no transistor. In the amplifying circuit, we need a transistor. We need a switching device there. So in the amplifier, we have a transistor along with other biasing components and along with other coupling capacitors. But in the feedback network, we are only taking a small portion of the output back to input. So it can be a simple resistive network or a capacitive network. And the output of this resistive or capacitive network, which is the feedback network, is a small fraction of the output. So Vf equals beta into V naught. So output is taken back, output voltage is taken back, given to the feedback network, and a small percentage of the output is available as Vf equals beta into V naught, where beta is less than unity, and then it is given in series to the input. You can see that the feedback voltage is given in series to the input. Now this is called voltage and series. Whenever you remember this voltage series feedback, visualize that voltage is taken from the output and it is given in series to the input. So the circuit which you are seeing at the left side is called voltage series feedback. On the other hand, at the right side you can see the same voltage is taken and the voltage is given in parallel or in shunt. Of course, the author is showing here, instead of the voltage source, he is showing the current source purposefully. Because otherwise, if there is this voltage source Vs itself, Vs and this voltage which is in parallel, they will have a contradictory effects. That is why the author is showing a current source here instead of the voltage source. You need not worry much about the notation of the current source here. Later on, when we derive the equations for all these circuits, I'll explain you in detail. So the left one which you are seeing is voltage and series. The right one which you are seeing is voltage and shunt. Shunt always means parallel. Now you can see the ratio in case of voltage shunt. A is V naught by II and beta is If by V naught. Because at the input, instead of the voltage source, he is showing current source. Why there cannot be voltage source? Because if this Vf is there here and Vf and Vs are in parallel, what will happen? When any two dissimilar voltages are in parallel, what will happen? Whatever is the largest voltage, that only will remain, right? Let me show you an example. Let me annotate. Let us say I have a battery like this. Let us say this is 2 volts. And let us say I have one more battery which is a feedback battery now. That means this feedback voltage. This side, let me show you. Let us say this is now 0.2 volts. And when we connect them in parallel, what is going to happen? Let us say connect them in parallel. What is going to happen? 2 and 0.2 are in parallel. What is going to happen? The net effect will be 2 only. Whenever there are two batteries of dissimilar voltages, when they are in parallel, whichever is the battery having the larger value, that only will be giving the output. This 0.2 will not have any effect. But what will happen to 0.2 now? 0.2 will be forced to maintain a value of 2. And there will be contradictory indications. That means maybe this particular battery may get damaged. The 0.2 volts battery may get damaged by means of this 2 volts battery. On the other hand, the 2 volts batteries may try to charge the 0.2 volts battery, and the 2 volts battery may supply a large amount of current to the 0.2 volts battery. In effect, both may get damaged. I am talking about a DC battery source. I am just giving an example of a DC battery source. There can be contradictory indications. There can be some calamity indications also. It can be dangerous to the circuit itself. That is why voltage series is simple. You can see here. Here these batteries are in series. See, the feedback voltage is in series with the input voltage. That way we have no problem. If there are two power supplies in series, we have no problem. And I had discussed this earlier also. When DC and AC are in series, we have no problem. DC will get superimposed on AC. But DC and AC are in parallel, AC will have no effect at all, because AC will be a varying one, DC is a constant one. So DC only will be dominant. Now when there are two DC sources of dissimilar value, if they are in parallel, there will be this calamity, or there will be contradictory indications. So in the voltage series feedback, we have no problem. Why? Because the feedback voltage is in series with the input voltage. But with the voltage shunt feedback, we cannot directly connect voltage with another voltage source. Now in such a case, it is better to connect this feedback voltage with the current source. Otherwise, as I have shown you here, let us say feedback is 0.2 volts, input is 2 volts, this feedback will have no effect at all. The feedback voltage will not be influencing the circuit's functionality at all. That is why voltage is taken as the feedback. Now voltage has to be connected in parallel to a current source. That is the reason he is showing you one current source. So I hope you understood this. Now because of this current source notation, we have the gain as V0 by II. It is not a voltage gain now. Here in the case of the left side circuit, gain is V0 by Vi. It is a voltage gain only. Whereas here in the right side circuit, in case of voltage shunt feedback, A is not V0 by Vi, it is V0 by II. We cannot say it as a voltage gain. It is looking like a resistance here now, because V by I is resistance only. But actually it is not resistance, because we have an amplifier circuit itself. So we will simply call it as gain only, but we will denote gain with a different ratio, because our current now is input. It is not the voltage that is input. Okay. Current is input to the amplifier and voltage is obtained out of the amplifier. We should visualize in that way. So A equals V0 by II. Similarly, beta equals IF by V0. Beta equals feedback current now divided by V0, because we have taken current source at the input. And I have told you in detail about why should we take current source here in case of voltage shunt feedback. I hope you have understood it. Let me stop annotating now. So you have seen now voltage series feedback and voltage shunt feedback. And the difference you have seen, in the case of a shunt connection at the input, we will always have a current source, we will not have a voltage source. Of course, all sources are basically power sources. We define them as voltage source and current source because at a time we consider only voltage or at a time we consider only current. Otherwise, all signal sources are basically power sources. They supply both voltage as well as current. Let me proceed to the next two feedback connection types, that is current series feedback and current shunt feedback. Always remember, whenever you say voltage and then series, voltage taken at the output given in series to the input. Whenever you say voltage shunt, voltage is taken at the output given in shunt to the input. So whenever there is a shunt connection at the input, we require a parallel connection there, and here when we have a parallel connection, instead of the voltage source we have the current source. Now let me proceed to the next two types. Now you can see these two types. Okay. Now at the left side you are seeing current series feedback and the right side you are seeing current shunt feedback. Now here at the left side, let me discuss the current series feedback. Instead of we taking voltage as the feedback, we are taking current as the feedback. So you can see, instead of V naught being indicated, it is I naught being indicated. I naught is equal to IL, that is being indicated. Now that IL is coming through RL and it is coming this way, and the current is coming into this feedback network. As I told you earlier, the feedback network is basically a resistive or capacitive network only. It is simply an attenuator network because we want to get a small portion of the output. Attenuation is the reverse of amplification. In amplification, voltage will be increased. In attenuation, voltage will be reduced. So attenuator network need not be having a transistor there. It can be a simple resistive network or a capacitive network, or a combination of both also is possible. Of course, when it becomes a combination of R and C, it is going to work like a filter circuit also. I had discussed about all these RC and CR networks earlier. So essentially this feedback network is either a pure resistive network or a pure capacitive network. Now, the circuit which you see at the left side is current series feedback, means portion of the current is taken back. Now you can always visualize, let me annotate here, because you may wonder what is going to happen in this way. RL current is coming like this, it is going like this, what is going to happen? As I have told you, this feedback network is basically a passive network. You can always visualize a resistor here, and you can also visualize a resistor here. You can visualize this way. Now when you visualize this way, see, current is coming here, output current is coming here, and it is going like this. Obviously, this resistance has to be of lesser value. Let us say if I call it as R1 and R2, if I call it this way, now R1, let us say IO. Let me annotate once again. Let us say we have this R1 and R2. Now this is R1 and this is R2. This is an attenuator network. By means of this network, we are sampling a portion of the output. And because we want current here now, let us say this current is coming like this, it is going through R2, going back to the ground of the amplifier, this manner. Anyhow, this is ground and this is also ground. This need not be ground. Okay, amplifier will have ground. So this way it is going like this. Now, portion of this is going back to the input through R1. So obviously R1 has to be much greater than R2 in this particular case. I am talking about this particular case. R1 has to be much greater than R2. Why? We already have RL here. When we have RL here, maximum current has to be supplied to the load only. If R2 is much larger, there can be a drop across this R2 and the supply of power to the RL can be reduced. So R2 has to be of much lesser value. So in effect, R2 must be much less than R1. Why R1 has to be greater? Because a small portion of the output only is going back to the input. That way we have this feedback network. Now through this R2, we are sampling the output current and then we are giving it back to the input. This is how we sample current. So you can see this loop. At the output side, you can see this loop. There is this current series. Now this current is in series with the input. Current can be in series with the input voltage. At the input, you can see the voltage source itself. Actually, the input current and the feedback current will be added together. So it is now current series. At the output, you are sampling current and you are feeding it in series to the input. Let me stop annotating now. Remember, whenever we have series connection at the input, it is voltage source. Whenever we have shunt connection at the input, it is current source. You can easily remember it this way. The reason for the current source I have told you already when I showed you the previous circuit. Now you can come back to the left side circuit and you can see that here A is I naught by Vi, because it is now not a gain, it is like a conductance here. I by V is conductance. But again it is a gain only. Why? Because we are now considering the output current and we are feeding it back to the input voltage. So A equals I naught by Vi. Similarly, beta equals Vf by I naught, because we are sampling the output current. So you can observe all these changes in the notations. Coming to the last feedback connection type, that is current shunt. The same thing is applicable here. You will have to visualize that R1 and R2 here. R2 is much less than R1. You will have to visualize that. But we are taking the output current and we are feeding back in parallel. Now again, when we connect it in parallel, when two current sources are in parallel, there is no problem. Only when there are two voltage sources are in parallel, we have problem, because voltage is going to be steady there. When two current sources are in parallel, it is simply like a Kirchhoff's current law, where two currents are going to join together, it is going to become a net current there. So you can see here, If and Is are in parallel. So it does not really affect the functionality of the circuit as such. The two currents will be added up. Okay, so you can see here the changes in notation. Gain A is now I naught by Ii. It is not a voltage gain now, it is a current gain, because it is a current shunt feedback where current is sampled at the output and it is connected in parallel to the input. Whenever we have parallel connection at the input, it has to be a current source. So A equals I naught by Ii and beta equals If by I naught. So in this way, we have seen 4 feedback connection types: voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback. Okay. If you have any questions, you can ask me. Otherwise, I will proceed. Okay. If people have no questions, I will proceed with the next discussions about how to derive the equations for each one of them. I will not be able to complete all of them today. I will be dealing with them one by one. Now when we derive the equations for all these four, then whatever is those 6 advantages of negative feedback which I had mentioned earlier, that will be evident now when we have mathematical analysis of these circuits. So now we have a table here. Let me show you the table because before proceeding to the derivations. I hope you can see this table. Summary of gain, feedback and gain with feedback from the figure, whatever is the figure shown. For voltage series, gain without feedback, that is A, is V0 by Vi. Gain without feedback for voltage shunt is V0 by Ii. Gain without feedback for current series is I0 by Vi. Gain without feedback for current shunt is I0 by Ii. My dear students, you will have to write down all these block diagrams which I showed you now. You will have to go through the textbook now. You will have to write down and you will have to practice these things on your own. If you do not practice, you will not be able to remember these many things. Okay, this is, even though they are simple, as students you will have to remember all these things. For remembrance, you will have to practice it. There is a question here. In diagram D, feedback is entering into the beta system. So then why is IF current shown in a direction which is entering the feedback system while not a direction coming out? Let me show you the circuit there. So your question here is, feedback is entering to the feedback network. Okay. So then why is IF current shown in a direction which is entering the feedback while not in a direction coming out? Okay, you are talking about this IF, right? IS is shown upwards where IF is shown downwards. That is your question. Fine. The answer is, now this is negative feedback. It is not a positive feedback. In a negative feedback, we will purposefully supply the input in the opposite direction so that we want to reduce the gain, right? That is the answer. If it would have been positive feedback, then the current's direction would be upwards. But now this is a negative feedback. That is why later we will consider as II plus IF equals IS. We always will have a phase shifting network in this feedback network also. That I have not yet told you. See, okay, because you asked me the question, let me elaborate this now. Let me slightly zoom this. Now, in all these four feedback networks, you know that amplifier is going to give a 180-degree phase shift, right? Let me annotate. In all these networks, amplifier is going to introduce a 180-degree phase shift. That means if the input cycle is like this, then the output signal will be like this, right? Irrespective of the feedback connections, even though I am showing you in the current shunt feedback now, you don't have to worry much about the waveforms. Now, when the input is rising, output will be falling in the case of a regular common emitter amplifier, and the amplifier is going to give 180-degree phase shift. Now, when you take the feedback here, now this feedback network is not going to introduce the phase shift. The feedback network is simply a passive network. Let us say in this case, it is not going to introduce a phase shift. If it is not going to introduce a phase shift, a small portion of the output will come here now. You can see the output waveform itself is coming here now. Now you can see the small portion of the output waveform is connected along with the input waveform. Now you can see that the input waveform is rising, output waveform is falling, and input waveform is rising, even the feedback waveform is falling. So what will be the net effect at the input? The net effect will be that it will be reduced. Now this is a small fraction. This is a slightly larger. Input is slightly larger than the small fraction. I have told you that beta is always less than unity. So when it is a small fraction, this small fraction which is anti-phase with the input, when it is anti-phase with the input, effective input to the amplifier is going to be reduced. That is what is negative feedback. anyhow we will have the gain that is reduced. That's what is negative feedback. For this reason only, these currents are shown in opposite direction. The same thing will happen in voltage also in future. In future means when I discuss the derivations for all these four circuits, you will understand that we are going to consider all of these four networks with the negative feedback only, not with the positive feedback. Now, if you want it to be a positive feedback, then here in the feedback network, it has to introduce additional 180-degree phase shift. It has to introduce additional 180-degree phase shift. I am writing with the mouse with a lot of difficulty. Okay, but we are not discussing that right now. That comes only in oscillators. At that time, let me discuss about positive feedback. Otherwise, all these four circuits are basically for negative feedback. I hope you got the answer.